saw about the yarn, right? It has two component, resource manager and node manager,
Yes.
and it has scheduler and the application manager, and it has application master and the container. So the scheduler is responsible for allocating resources to various running applications, right? And scheduler has the policy that we saw yesterday, right? Capacity scheduler, fair scheduler, and FIFO. These are the policy which it is using for the scheduling the job. Then application manager, it just keep the list of applications which are running, currently submitted, or those things. And also manager only accept the job submission, and also the first container for executing the application. What it means, like whenever you submit any job, okay, this application master will first start one container, okay, and then after that it will, once it start the first container, after it will negotiate the resources with the application manager that I need these much resources, give me that. So once that application manager give the resources, then only application master will start running the job. So application master is running responsible for running the job end to end, like negotiating the resources and keep running the job, and then it will send the heartbeat and the status to the application manager, that what happened to the job, what is the status and all those things. And once the job is completed, application master will that is the only responsible. Once the job is completed, that's it. Then again, once the new job come, then new application master will come into the picture. New application master will start, and then again it will take the start first container, and then it will negotiate for the resources, and then it will run the job once it get once the resource is allocated to this. Yeah, these are the things. Other than that, we were yesterday we were at the FIFO. These are the similar thing it has mentioned, like how client is submitting. And then one more thing I told you, right? Node manager was keep sending the heartbeat to the resource manager after every interval, so that with that resource manager will know that okay, this node is alive or not. If in some interval, if you don't, let's suppose in 10 minutes it won't get any interval from it, then it declare this as dead. And then we look at the scheduling in yarn. There are three types of scheduling: FIFO, capacity, and fair scheduler. In the capacity, we have one separate queue for the smaller job, and FIFO is first in, first out. Like what if you have ABC, then A will get the first all the resources. One is completed, then second job B will get, and then third job C will get. And in the fair scheduler, if you have three job ABC, then all the job will get the equal share of the resources. So that's why we call it the fair scheduler. Yesterday, I showed you like in your you can have queue, and you can assign like how much you want resources. You want to assign the resources for them. Like for the support, maybe you can give like 10%, and for the engineer like 60%, or marketing 30%. So you can, let's suppose you have 100 GB of resources. So you can divide your resources between the team. See here, as you can see, we have three queue, and we call as at a queue. Let's suppose that if we assigned resources to a queue, and whenever support team will submit its job, it will use the Q1. Let's suppose Q1 is given to support job, and Q2 is given to the engineering, and Q3 is given to the marketing job. So whenever they submit, they will use the queue that I'm submitting in this queue, and maybe on this queue, one access is given to the only the support engineer, something like that we can do. Okay. Okay. This is, you can see like in the fair scheduler. Uh-huh. Job one submitted, job two submitted. See, in the fair scheduler, resources are, let's suppose what happened that in the beginning, okay, your job is, you submitted job one. So in the beginning, it will take all the resources. Let's suppose this is the resource you have, and you submitted job A. So job A will take all the resources because nothing is running. But when you submit the job B, it will started allocating the half of the resources to B job. And when you submitted job C, then it will start again allocating the resources from them to the C job. When if suppose nothing is running, then maybe all the resources are taken by the first job only. But if something comes, then slowly it will start allocating resource to it, and A will free some of the resource or half of the resource for the B. And similarly, when the C come, it will start sharing the resource with it. These are the just the terms preemption. So what happened, as I told you, right? When you submit a job, and let's suppose that you have three jobs, right? As I told, A, B, C, right? And you submitted job A. Job A has taken all the time or all the resources. Then you submit job B. Then what happened that resource A will start allocating to B, and it will take some time, right, to allocate job to the, let's suppose you have these big resources, and A job has taken all the resources, and then B has come. Then it will start allocating job by killing the containers. Okay, so I told you, right, jobs are running in the containers, right? So
Yeah.
let's suppose that A has it is using full resources for this container. Then if the B come, then it will start killing some of the container and allocating resource to the for the B. Okay, so once that resource B by that time, when it kill the resources and then start allocating to the B, then it will take some time. So that time we call as the preemption.
Okay.
Okay. And then the Q elasticity is like, so in the capacity scheduler, this elasticity is the term with the capacity scheduler. If there is more than one job in the queue and idle resources are available, then capacity scheduler may allocate the spare resource to the job in the queue. Uh, See, let's suppose, let me give you an example. You have assigned, this is the resource, and you have assigned this resource to engineer, marketing team, and this much resource to engineering team, and this much resource to sales team. Okay. So actually, let's suppose at some point of time, only marketing team is running the job. Okay, and sales team and engineering team are not running anything. So at that time it is better that, see, either if no one is using that, then this resource will be idle, right? If I'm not using, then this resource will be idle. So just for the better capacity utilization or the utilization of resources, what I will do, I will use the resources of the engineering. Market job can use the resources of the engineering because nothing is running, and during the because the resources of engineering and sales are idle. So what marketing will do, marketing will start using the resources of sales and engineering. So that's we call as the q elasticity. See, I have assigned it only 10% of the resources, but it started using the engineering and sales. Maybe it started using the 40% of the resources during the idle time when engineering and sales are not using the resources. So that thing we call is the q elasticity. See, even that caused the queue capacity to be exceeded, right? Because my queue capacity is only 10%, but I'm using 40%. So this is causing queue capacity to exceed. So this we call as the queue elasticity.
Okay.
You got why we are using this queue elasticity?
Yep. Yep.
Okay. Delay scheduling. I have told you this delay scheduling in the while during the Hadoop, right? That if I have two node, or let's suppose I have three node. Okay. So and let's suppose all the this has table A and table B. Okay, and this has table C, table D, something like that. Okay, and let's suppose you want to use the table A. You have some new job which need table A and B, and this resource and this cluster is already being used by the some other job. So that time, either it can wait till the job get completed, or it will start on the other node. So if it start on the other node, then it has to move the data, right?
Yes.
So this when it wait for some time so that this resource get available, and then I will run my job here. And this we call as the delay scheduling. And why it is waiting is like the local requirement. We call it the local. What was the term? I think in the Hadoop we saw data locality. Okay, data. We call it as data locality.
Okay.
Okay, if I'm running on the job near to the data, that we call as the data locality. So in that case, I don't have to move the data. So that's what here it is mentioned. It has been observed that waiting for short time can increase the chance of being allocated a container on the requested node. This increase the efficiency of cluster, right? If I'm if let's suppose I wait for some time, right, 2 3 few seconds, and then I got this then I got the resources from this cluster, then what it has been observed that it actually increase the efficiency if I wait for some time. Like, see, either I wait for a few seconds, or I can have option of moving my running my job on this cluster where my data is not available. But it has been observed that if you wait for a few seconds, then you will get the resources, and that is more efficiency. If more efficient, like you can finish your job in less time. So that's why that delay when you wait for the resource to get that time, that we call as the delay scheduling.
Okay.
Okay, so these are just the term which you should know. Okay, what is preemption, queue elasticity, delay scheduling? These can be asked.
Okay.
So, dominant resource fairness is like now let's suppose you have job A, okay, and job B. So what you are doing in the fair scheduler, you are allocating resource half of to job A and job B, right?
Yes.
And your resources, uh, let's suppose you have in the job A you have lots of calculation like group by and all those things, right? And you are doing the sum using the window function and group by in job A. And in job B you have just the select, okay, and select statement. But the data size is very high in job B, and very not that big. Let's suppose in the job B you have data size of 100 GB, and in job A you have data size of 20 GB. But you have more calculation in job A and less calculation in job B, because you have to just select and filter in job B, but you have a lot of calculation like group by, sum, and window functions in the job A. Okay, so what you did here in the fair scheduler, you have 100 GB memory, and let's suppose you have 12 core of 12 core. So what you did, you divided 50 GB and 6 core to job A, and 6 core and 50 GB
Okay.
to job A, and 50 GB and 6 core to job B, right? When you have two job,
Yes.
this will do in the fair scheduler. But don't you see one issue? Like my job A, okay, it need more memory because it has higher data, like larger data. And this job A need more CPU or core, I would say. This CPU we need when we have calculation extensive job, like here we have group by and all. When we have just the filter and all, that time we don't need much CPU. We just need more memory. So in that case, if you see, right, we divided the core and the core CPU and the memory equally, right? 6 core and 50 GB. But if you assign more core to job A and more memory to job B, in that case, your job will run faster, right? So that's what one functionality in the yarn which you can enable, that we call as a dominant fair resource fairness. Actually, it uses the concept of dominant resources to compare the multi-dimensional resource. Multi-dimensional means it will not just directly divide the resource. It will check that which is the CPU intensive and which is the memory intensive. If it is job A is memory intensive, or job B is memory intensive, I will assign more memory to it. And as it is calculation intensive, I will assign more CPU to it. Got the thing?
Yeah.
See, one application needed little CPU and lots of memory, and other required lots of CPU but little memory, right? But in this case, what we were doing, we were assigning half of the resource memory and the CPU to both. So that is not the good. Means if in that case, our job will not run the efficiently. This will also run slow because I have assigned the less memory, and this is also run slow if because I have assigned the uh, less CPU. So maybe in this case, what I can do is like, let's suppose that I'm just giving you example. You can assign 80 GB to because job B is needed more memory. So I will assign 80 GB and let's suppose 4 core to job B, job A, yeah, job B because it is 100 GB of data. And I will assign uh, 20 GB, and from this I left with 8 core to job A. Okay. So in this way, I am fairly distributed the resources as per the job requirement. Not see here in the fair scheduler, we were just directly distribute the dividend. Let's suppose if I have two job, I will divide the resource into two part and will equally I will assign. But DRF is one property, okay, or one thing. If you enable in the yarn, then it will use the multi-dimensional resources to distribute the resources. This is just the example. Same thing, what I've told you that is mentioned here. If job A is CPU heavy task, use a memory heavy task. In that case, DRF attempt to equalize CPUs here. So these things you can read, okay? One more thing, in the capacity scheduler XML, okay, you can make these changes. In the yarn, see it is mentioned the capacity scheduler can be configured to use DRF by setting yarn scheduler capacity resource calculator to this one. This if you make these changes in the config file of the yarn scheduler capacity resource calculator in the capacity scheduler XML, these are the files. If you look at the yarn, if you download yarn and extract, you can install yarn also in your laptop. Okay, but I would say not required. Just work on the Spark. But you can it this is the place where you have to make the changes, and this is the change what you have to do for the DRF. Or by default it is not enabled. By default in the fair scheduler it will just equally divide the job. But if you want to be the multi-dimensional resource should be divided based on the multi-dimensional requirement of the resources. Like here we have the job A was needed more core and job B needed more memory. So in that case you can enable that using this. And in the fair scheduler, DRF can be enabled by setting the top level element default queue scheduling policy, allocating file to DRF. These are the configuration. Okay, we don't need this much. Okay, just for the knowledge it is, but you anyway, these things were done by the ops, so you don't need it. But just for the knowledge, you should know what is DRF and if you can do that or not. Got the thing about DRF,
Yeah.
fair scheduler, capacity scheduler, everything, right? I will share this with you. You read
Yeah.
it, many things in between, you will understand. Okay, now let's move to the RDD. Okay, let's just cover RDD today, and then tomorrow we'll start Spark, and from Monday we will start Scala.
Okay.
Tomorrow I want to start Scala. Maybe on the Monday, from Monday we'll start Scala, and those 4 days we'll learn Scala, and then we'll move to programming.
For Scala, any prerequisites required?
And no, you don't need anything.
Okay.
Uh, One more thing you can do, just uh, try to see how you can connect in. You have IntelliJ, right, in your laptop?
Yeah, I
If-
have done it yesterday
Yeah.
only.
Okay, if you have, just try to see how you can connect your IntelliJ to the Spark.
Okay.
Okay, just try to see it is. I think it is doable. You can connect your IntelliJ to the Spark. Then it is easy for you. You can just write your program on the IntelliJ and run on the Spark. We have already seen these slides, right? That it has a Spark core, Spark SQL, and Spark streaming. Currently, now I'm going with the RDD Spark core. Okay, I will then tomorrow I will cover Spark SQL optimization, and then from Monday we will start Scala, and then we will look at some of the code of while learning Scala, we'll look at the RDD code and Spark SQL code, and after that we'll learn the Kafka, and then once after learning Kafka, we'll move to the Spark streaming, and we'll see the in the Kafka also we will have some code for the consumer and producer, and then the Spark streaming. And then once I complete the Spark streaming Kafka, then we have very few things left. Okay. Uh, in that case, if you want, we can take a break of in between so that you can practice the Spark, because once I teach you Spark streaming, that is the most crucial thing of this syllabus of this topic. Okay, because these days Spark streaming and streaming is something which most of the company asks. So just keep learn well these three. Anyway, all the things are important, but previously not much company are asking for the Spark streaming, but nowadays people are asking for the real time. Okay, so you should learn these three. Once we finish this Spark streaming, then we'll have some few topics like Airflow and the machine learning. Okay, so if you want in between, you can take a break. Okay, and then you practice at your home. Or if you want to finish the course, then I will finish, and then maybe you can take your time. If you need anything, then you can ping in the group. I will help you with that.
Sure. Also, these would be libraries.
Yeah, these are the libraries available in the Spark.
Okay,
If you
okay.
if you if you connect your IntelliJ with your Spark, you have to just use the library of the Spark SQL and Spark streaming, and then you can write it.
Okay.
Like how we have libraries in the Java, right?
Yes.
Similarly, we have you can just use the Spark SQL library or Spark streaming library while writing the code.
Okay.
This is also one important thing you should know. This architecture we already have covered. Okay, this RDD actually it is the fundamental unit of a Spark. Everything under the hood is using RDD. Whether you use the Spark SQL or any library, under hood it is RDD which is working. So what is the RDD? It is resilient distributed data set. Now, why we are calling it is resilient, we'll see. Distributed, why we are calling it distributed? Because As I told you, right, we have multiple clusters. And if you have, let's suppose you have a table A which you want to process and it is 100 GB of data, right? Then it will divide it into the, okay, now let's just see how it will divide it, the data onto the multiple cluster. And each, let's suppose it will divide it into the 10 partition. The division we call it the partition. Okay, you will see, you will heard this term lot of the places in the Spark, the partition. So partition is when you divide the data into, let's suppose, 10 parts. So each part we call as the partition. So how you divide the data is like, let's suppose you have this table, right? So horizontally you divide. Let's suppose you have 1 to 100, right? Data row number, or let's suppose some primary key. Then what it will do, it will do 1 to 10 on one cluster, 10 to 20 on one another cluster, 20 to 30 on another cluster, something like this it will divide. Okay, so that's we call as the, and each division we call as the partition. So why we'll call as why we call it a distributor? Because it process the data, it divides the data, and it will process on the multiple cluster. So that's why we call it a distributed, because we distribute our data on the multiple cluster. Now it is fault tolerant. That's we see. Distributed we understood, like, because it is on the three different clusters. It can have, like, let's suppose if I divide it into the 10, then it will run on the 10 cluster. Now, how it is resilient? Why we call it resilient? If the data in the memory is lost, it can be created. So let's suppose that we are running on the multiple, let's suppose on this, you are getting me, right? You're following me.
Yes. Yes.
So let's suppose I have data on these three cluster. Let's suppose I divided my 100 GB data into the three part and I'm running on it. So let's suppose something happened to this cluster. Okay, then what it will do? What Spark will do?
Cluster. Next one.
Yeah, what it will do? Tell me. I have told you. I think I remember. I have telling you these things.
Cluster.
Let's suppose
Next
I'm
one will
running it
be.
on one cluster and it failed.
It will use the next one.
Next one, which next one?
Okay, which next one?
Next one, which has data, right?
Ah, yes, gender. Yes.
It know that where the data is present, then it will run where the data is.
Yeah, for that we have another node.
Right. So now the thing is, let's suppose what with this, what I'm trying to say you, let's suppose that on this node goes down. And okay, one more thing, these all three processes, let's suppose I have divided the data, then I think I have told you also that all these three will run parallelly at the same time, right?
Yes.
Yeah, so these three will run parallelly. Let's suppose that it after running 1 minute, this job failed. So what will happen? It will start on another node. But you see, the thing is like, it don't have to compute these two again because these two has not failed, right?
Yes.
So that's what, if the data in the memory is lost, it can be recreated and recreated just for that partition, not for all. Okay,
Last means failed only. No.
right. Let's suppose something happened. I'm telling you that this node goes down, but let's suppose it was internet is running the on the some of the data, and data in the memory is lost, right? So okay, let's suppose that what I'm telling. Let's suppose I have three steps. First, I'm doing the map. These things we'll see in the RDD. What is the map? What is the filter? Let's suppose I have three part map. First, I'm doing. I took the data. Okay, I do some mapping on it. Then I do the filter on it, and then I do the group by. Okay. Let's
Okay.
suppose I was doing these things. So, and while doing the filter, something happened, right? Something happened on this, and this node goes down. Or I lost the data. So what it will do, it know that I have divided my data into the three partition: partition one, partition two, and partition three. Okay, and first partition was running on this, second partition on this, and third on this. So it will let's suppose first fail, so it will take the first partition. It know that okay, this partition is here also, so I will start on this, and these operation will be done on this. Okay, now Spark know that Spark actually keep Spark know that what are the operation I have to do. It was doing parallelly on all those things. Now once this node 1 goes down, it will just take that partition. Okay, I know that one partition, first partition was running on this node and it failed. Then I will look at the where the next first partition replica is. Then I will start running on the job, and I know that which things I have to. Driver know that which operation I have to do. So driver will run those operation on the map, filter, and group by on just only this partition. I don't have to recompute for all of it. So I just recreated it. Got the thing?
Okay. One second, please. This one.
Yeah.
Uh, you're saying something, Ravi?
Yeah. You got this?
This map will once again, please. Actually.
Okay. So the okay, one more thing. This we call as the lineage. I think I have somewhere in the slide. I will show you. But
Okay.
these things we call as the lineage. Anyway, we have these. We'll see that. For now, you just understand that. Let's suppose you have this data, right? You loaded into the Spark. Okay, and then something happened, and this node goes down, or this data I lost. So Spark know the data you loaded. Spark know that this is a partition. So this is the original data, right? Let's suppose this is the original data and divided into the three part. And first part I was running here, second here, first here, second here, and third here. Then I have this operation. First I have to read the data, then I have to do the map, then I have to do the filter, then I have to do the group by. So let's suppose I lost this. Okay. So Spark has your Spark once you read your original data, Spark know that only the first partition has failed. So from this data, it will again either it is stored, or it will from this your original data, it will again create the partition, and it will just run only on that partition. These steps.
Okay.
Okay. So that's what it is mentioned. If the data is lost, if the data in memory is lost, it can be recreated.
Okay. I'm
See,
in the
you
next
are
server. It will run.
sorry.
I'm in the next server. It will run.
Right, on the next server it will run. See, in the HDFS, you have the data replicated, right? But let's suppose that you have not the data replicated, okay. In that case, it may happen that you have loaded the data, right? Let's suppose if you load the data. See, replication and all things will be if you are running Spark on HDFS. Okay, let's suppose you are running Spark on HDFS, then replication thing and all those things are taken care by the HDFS. See, you have HDFS, and then you have Spark. Your Spark is running on top of HDFS. So replication things that I will replicate my data somewhere. Those things are taken care by the HDFS. Okay, it is not those responsibility Spark will not take care of.
Okay.
See, with this Okay, for now you just understand that the resilient data in memory is lost, it can be recreated. Distributor you understood because I am running it on the multiple cluster. And now one more thing, RDD is immutable. Let's just go to next. Immutable, somewhere I've written. RDD is immutable. Yeah, RDDs are immutable. What it with mean is like, let's suppose I showed you, right? I'm doing the three operation for map, filter, and then group by. Right? These are the operation I was doing. So with immutable means it cannot be updated or it cannot be changed once it is created. Let's suppose I have my data, okay, and I did some of the mapping on it. So mapping will create a new RDD1. Then I will apply filter on it. Then filter will create another RDD2. And again on this group by I will perform, then group by we create another RDD3. You cannot update the RDD. This means, let's suppose you are after doing the mapping, if you think that okay, I will do the filter on top of the RDD1 and I will change the RDD1. No, it cannot happen. Each steps it will create the new RDD. RDD is immutable. See why we are doing that? Immutable means they cannot be changed after they are created. And why we are doing that? So that I can rule out the potential problem of the updating from multiple thread at once. Okay, so that's why RDD are immutable. And RDD are distributed, I told you, right? Each RDD is broken into multiple pieces called partition, and these partitions are divided across the cluster. I told
Okay.
you.
Yes, yes.
And these things are automatically done by Spark. You don't have to do anything. You have to just know that what it is doing.
Okay.
Okay. Okay. RDD is encapsulation is the capsulation around a very large data set. So RDD you can create either new RDD by transformation of existing RDD. I told you, right? When we have map, these we call as a transformation. Map, filter, and group by, these we call as the transformations. There are two things, transformation and action. We'll see that about that also. Okay, we have the slides. When we start reading the Scala, we'll look at this programming ops also. So one more thing, you have two thing in the Spark: transformation and action. And this Spark is lazily evaluated. Means until unless you perform some action, it won't do anything. Action is like, one action is collect. We'll see this about these things. There is one action called collect. So let's suppose you created this lineage graph, map, filter, and group by. Okay, and until unless you give the action on it, it won't do start work calculating the things. If this will call as the lazy evaluation, we'll see it. We have these things later further. Okay, this we understood, automatically done by Spark. See, under the hood, Spark will automatically distribute the data containing RDD across your cluster and parallelize the operation you perform on them. I told you, right? All the things will be done parallelly. That is the reason it is, see, two things. Spark is, if the question is why Spark is faster, that it is in memory and doing everything parallelly, right? But when I compared with the Hadoop, Hadoop was also doing the things parallelly, but it was not doing the in memory. Got it? This we saw. In case of any node cluster, in case of any node cluster, Spark recover the part of RDD from the input or pick up from your left, right? These things we saw. Okay, there are one more thing, cache, like cache and persist. Let's suppose that you have used the cache here. Like cache means you are storing your final output till here. So let's suppose you cached it and your step fail on the group by. Okay, in that case, your Spark won't again do the calculation of this. It will just because you have stored your data in the cache, it will start from here and then it will just do the group by. Okay, those things these things we call as the cache. And persist, there are two things, 𝐶 and persist, that also we'll see. I'm just telling you these things because we are going through it. So 𝐶 also we have, there are five type of persist, that also we'll see. See, you understood about the RDD, that it is how it is resilient, how it is distributed, why we call it the resilient and distributed, because that is the one of the interview question. What is RDD? When you say that resilient distributed data set, they will ask you why it is resilient, why we call it the resilient. Distributed anyway, they may ask you, but distributed is like it is running on the multiple cluster, but why it is resilient? That is the question. And RDD is immutable. This that is also you should know. And RDD can be created from another RDD. Somewhere it was mentioned. I'm looking for that. Okay, RDD can be created from either reading the data set or from another RDD. As you can see here, right? I have created after doing the mapping, I created one RDD. After doing the filter on this, I created another RDD. So RDD can be created by doing by the transformation on another RDD. This is transformation, right? So one RDD is created by doing the transformation on another RDD. On RDD1, we do some transformation, okay, and it will create the RDD2. Got it right?
Yes. Yeah.
Okay, so we'll read about the transformations and action, but let's just finish with this slide. So there are two type of operations on the RDD. One is we call it the action and transformation. Transformation create the data set from current one, and action return the value. Until unless you perform some action, it won't return you the value. We'll see that what are the actions and what are the transformations, but there are two type of operation, action and the transformation. So transformations, I told you, right? You do some RDD, you do some transformations like map and filter, it will create the new RDD. So this we call as a transformation, and action is, there are multiple actions. One is like collect, and another is take. If you do at the, so action, okay, one more thing, action is always at the end. After all your transformations are done, let's suppose I did some of the transformation, one more transformation on it, okay, and then I did the RDD3. And then after that only I can perform action. Your action is your last thing, because action will give you the result of these transformations. Okay, I think we'll see here it is mentioned, right? Transformations are, these are things, and then we do the action, and then it will give you the result. Lineage also, I think we have in one of the, this is also one of the important concept. People will ask you what is lineage in the RDD. We'll see that. Lineage and DAG, these two also you should know. Directed acyclic graph, I think I have told you, it is creating one directed acyclic graph, but we'll go a bit in depth about it. What is lineage and what is DAG, how it is making it fault tolerant and optimizing the performance and all those things.
We'll just a question. So we'll be doing a small project, right?
Yeah, we will be doing the project at the
Um,
end. Once
okay.
we cover everything, I will give you some time, okay, for you to practice, and then at the end, we will be doing. There are project we'll do. Okay, okay. No, anything else?
Can you please share the document, this
Okay,
document?
I will share that on the WhatsApp.
Yeah. Thank you so much. Yeah.
Thanks. Bye.
Bye.